Okay, so on this, now let's talk about this for a second. So we had done a whole bunch of problems on this assignment where they had not been specific. They had said things like, in terms of f of x, if g of x is going to translate f of x down 14 units and to the right by 10 units, what would g of x be just in terms of the generic f of x? Let's everybody just click these all the way close, please. So what's that going to do? What does this part right here do? If we're going to translate down 14 units, what's that do? Yes, sir?
Subtract 14.
Okay, so I'm going to subtract 14 from the whole thing, right? So we've got our function f of x. And we're going to subtract 14 from the whole thing to move it down 14 units, because we said that a vertical shift means that we're going to add or subtract a number that we call k, right? That's the number we give to this for vertical shifts. That parameter we call k. And we said that we're going to add or subtract that to the output, meaning the whole thing, right? So it's outside of the function, just some number that's added or subtracted. Okay, what about this part right here? What if we want to shift to the right by 10 units?
Add 10.
No.
Wait,
Subtract.
subtract.
Okay, subtract 10 where? From the whole thing?
No,
No.
from the x.
Okay, from x, because when we do a horizontal shift, we're going to add or subtract a number to the input itself, right, to x. Remember, this is backwards. We're always going to subtract from x the amount of the shift. Well, this is a positive shift, so we're going to subtract positive 10, right? So we would just do a minus 10 right there. Everybody agree? Okay, and that stuff was no problem. People went through that no problem. I did get some questions, though, when we got to the last 3 questions, understandably.
Yeah.
This is a little different. This time we've got a function f of x that's not generic. It's specific. It's a cubic function. F of x is equal to x cubed. Okay. Now let's think about this. We're still kind of people are getting much better at conceptualizing functions. But let's think about this in terms of the way a function behaves. What are the parts of a function? If we just look at this simple function up here, what are the things you can tell me about this? What are the parts? What's the anatomy of any function?
F of x equals
Yeah, so just tell me what's that part right in there called?
y.
Input.
Okay, that's the input, right? Right, so that's, just this part in here, this is telling us that we're going to input x values, right?
Yeah.
What do we call this part over here? Remember?
Output.
Say it again.
Output.
Well, kind of. It's how we calculate the output. We call that the rule, meaning that's the formula we're going to follow to calculate outputs. Does that make sense? So we're inputting x values. We're going to do this to them, right? And then when all's said and done, this is how we calculate f of x, is how we calculate the outputs, right? Does that make sense? Okay. So this is telling us for values of x that we input, we're going to cube those values. What's f of 2?
Like for that problem.
Just for this function,
Oh, 8.
it's 8. How'd you get that?
Because I plugged 2 into the x on the other side.
Okay, good. We plug 2 in for x. If f of x is x cubed, f of 2 is 2 cubed. What's f of a?
A cubed.
A cubed. Because the rule tells us whatever I input, I'm going to cube. What is f of the quantity x minus 10?
10 cubed.
No.
Wait. What?
If I put, what's f of hand is just hand cubed. Whatever I'm inputting, I'm going to cube that thing, right?
Yeah.
So if I'm going to input an x minus 10, the whole thing, and in math when we want to include the whole thing, we call it a quantity, right? So if I'm going to input the quantity x minus 10 into my function, what do I do with it?
Cube it.
Say it again.
X minus 10 cubed.
Good, x minus 10 quantity cubed. We're going to cube the whole thing, right? So what this is really equal to in terms of our specific function then, this looks like, now tell me what I'm doing wrong. I need parentheses. What am I telling the math gods here?
It's just like
It's just x minus 1,000, 10 cubed, right? That's not what we want. we want the whole input x minus 10 cubed. And then this minus 14 doesn't change at all. That's outside the function. Okay, you get the idea? So then what we did here, I mean, we kind of looked at this in two steps. We started off with a generic f of x, and then we applied it to our specific x cubed. We don't have to do that, though. We could just jump right to this answer, right? If we know that f of x is x cubed, and we want to move to the down by 14 units, we could say g of x is going to be our x cubed. Outside of the function, we're just going to subtract 14, right? How do we apply to the right by 10 units? Well, inside the function, that means in here, right? Does everybody agree this is what's inside the function? This is a cubic function, right? We're cubing stuff. So inside the cubic function, we've only got an x right now. But if we want to go to the right by 10, I've got to replace that x with an x minus 10. Right? So we can just go right to that answer. Okay? Everybody see that? Okay? All right, so then the next step is I want to draw your attention to something else. There's another assignment I put up for 2.1.
Can we open our computers?
Yeah, go ahead. So the purpose of this assignment, if we pull this thing up, let's just look at a couple sample problems here. What if we do something like this guy right here? Okay, so what's this saying? If we take a square root function, the parent function, f of x equals the square root of x, looks like this. Okay, so everybody focus up here now. I know you got those things open, but we got to train ourselves. Well, you got to be going on those in just a second. Have you practice this? I want you to see something really important here. This is not like a major difficult algebra procedure. This is more of a concept that I really want you to get this thing straight. I want you to be able to equate these things in your mind because we're going to be doing this all year long. So if this is a parent graph, right, we could describe the parent graph. What are some characteristics if we had to describe to somebody how to draw the square root of x? Where does it start?
0.
It starts at 0, 0, at the origin, right? So that's an important point. That's what we could call the initial point of the function. Or we could just call it a special point if we want to, right? But in this case, initial means beginning. So the initial point is at 0, 0. And then it looks like as it moves up, the slope is decreasing. The steepness of the hill is decreasing. One important thing, though, might be useful here. It's going to be useful today. If I go over 1 to the right, how far up do I go?
1.
I go up 1. And that makes sense, doesn't it? Because if I go over 1 to the right, what I'm really doing to calculate the y value is I'm taking f of x and I'm inputting an x value of 1.
So it's squared?
So it's the square root of 1, right? F of 1 is the square root of 1, which is what?
1.
1. Good. So we go over 1 and up 1, right? We would go over 4 and up how far?
4.
If I input an x value of 4, what does this function f of x tell me to do?
Square is 12.
Square root it. Okay, so square root of 4 is
2.
2. And notice what we get. We get coordinates over 1, up 1, over 4, and up 2, right? Does that make sense? We could say that let's let this one be a really convenient second point for us if we want to graph a square root function. We start at the origin and we know we go over 1 and up 1, and that kind of guides our sketch a little bit, right? Okay, so what about this though? What if we want to do this to the function? And here's where I want you to really think about this. If I'm going to do that to the square root function, let's look at what those numbers do. What have I done? What is the minus 8 doing to the parent function f of x? What's that minus 8 doing? So this part, what's that doing?
Making it go down 8.
Makes it go down 8, doesn't it? Everybody agree?
Oh, and that would make it go
Left.
Yeah, left by 7, right? See this part right here, if I subtract 8 from the whole thing, right, from the function, that means we're going down by 8. And if I
Add 7
to the input, that means I'm going to the left by 7. Everybody agree? Okay, now that's all the points on the function, but what if we just focus on the really convenient point, the starting point, or the initial point? What does that tell us? Where's it going to end up? It started at the origin, but for g of x, you just told me the two things I'm going to do to the whole function. I'm going to take the whole function and go down 8 and left 7. What about this starting point? Where would it end up then? What would the coordinates be?
Down 8 and left 7.
Okay, so what does that look like in terms of an ordered pair? Yeah, it's going to be the x goes first, right? So it would end up over here at -7 and then down 8. So it's going to be like right there, isn't it? I'll color code these. So we got, oops, purple. So we got -7, comma, and then the orange one you guys told me was -8, right? Everybody agree? We've done two things. We've taken that original point and we've gone down 8 and we went left 7, just like you told me, right? Okay, so we don't really even have to, and what would the rest of the function look like from there? We could just start there and draw it. If I start at my initial point and I go 1 to the right, how far up should I go?
1.
1, just like before. Because I've just dragged this parent function. Everybody agree?
Mm-hmm.
Okay, so then I'd go over 1 and up 1, and I'd go over 4 and up 2, and I would just get something kind of like that, wouldn't I? Right? Okay, so do we even really have to think about this as starting with a parent function and dragging it? Not really. You see the jump we're going to make here? We could say, okay, if I take a function like a square root function, where we have f of x equals the square root of x, and I'm going to let g of x look like this. I'm going to let it look like the square root of x minus h plus k. What do the numbers h and k represent?
K is like vertical, right?
K is vertical, right? So that's like a vertical translation. If k is positive, we're going up, negative, we're going down. H is the horizontal translation. But instead of thinking of it like a translation, what could we say about the coordinates of the initial point? They started at 0, 0. So if I'm going to translate the initial point horizontally by h and vertically by k, doesn't it end up at hk?
Yeah.
Right? You see the point of this thing. And we're able to say if I ever write a square root function in that form, it's telling me whatever number goes there, call it h, is the x coordinate of the initial point. Okay, let's close these up. I just look out there and I know I would be the same way. It's just such a distraction, such a temptation to get distracted. But you got to get this communication. Whatever number sits there, call it h, that's the x coordinate of the special point, the initial point in this case, right? That's the y coordinate. Okay? So for a problem like this then, where is it? I mean, that's all they're asking here is the initial point of this square root function is at what point? You already told me. Well, right there. -7, -8 as an ordered pair. That's exactly what we would input in Moodle, right? Let's try another one. It's not like this is some big profound thing, but you see it's just a different way of looking at it. Okay, so let's try... How about one like this? Totally different kind of function, right? That is a cube root function. A cube root has a different look. We'll talk more about cube roots later, right? But for now, the main thing is, this time there's a different kind of special point. The special point isn't the initial point, it's not the starting point, but it's kind of the middle point. What it really is the point of symmetry of this function. If I rotate it around that point, I could spin it half a turn and it would overlap with itself, right? So we'll just call it the special point. When we eventually talk about cube root functions, that's going to be a really key point for us, okay? You tell me right here now, where is that special point going to be? If I want to draw a cube root function corresponding to this function up here, g of x, all I want to know right now is where's the special point going to be? It's not accidental that it's the point that starts off at the origin normally. So where is it going to be when I do this to it? What's the x-coordinate of the special point going to be?
-3.
-3. How do we get it? Because that's the number being subtracted from x, right?
So we wouldn't even worry about the negative or -1 yet?
Not yet. What's the -1?
Down 1.
That's down 1, right? So that's the value of k, isn't it? That's going to be the y-coordinate. So where is this going to be located? The special point is going to end up at the point -3, -1, right? If I had to write just all possible cube root functions in terms of h and k, couldn't I just write it like this? I could just say something like g of x equals the cube root of x minus h plus k, right? Everybody agree that the value of h there is -3, right? And the value of k is -1. So we got a new parent function, but something that looks very much the same. In fact, we could be very generic about this. We could say, for any parent function, this is always going to be true. If f of x is the parent function, and we write g of x this way, what are h and k going to represent? Well, they're going to be horizontal and vertical shifts, but they're going to represent the final location of any point that started off at the origin, right? The points that start at the origin for every parent graph that we deal with are the crucial points anyway, right? So it works out great for us. Whatever special point starts off there is going to have those coordinates when we're done. Okay, let's look at another one.
So can we enter that into Desmos?
Yeah, yeah, you could, yeah. But you don't need to. You can look at this, like for a problem like this, we just look at this and say, okay, what's being subtracted from x? -3.
So
they
just want the x and the y, not the
Yeah, that's it. All they're wanting is, they're wanting the special point of this cube root function compared to the parent function down here that's graphed.
All right.
The special point, you'll notice on all these functions, it's going to start at the origin, right? Let's do another one. Okay, this time this is a cubic function, but where's the special point starting? 0, 0. So once we're going to take that parent graph, which we'll get familiar with later, right? And if I want to do this to it, right, I want to create a new function, a new cubic function, I'm always going to start when I make a graph of one of these functions at the special point. That's going to be our home base, and then we'll from there we'll make a sketch based on the, what the parent graph looks like, right? So where's home base going to be here? Where's that special point going to be?
7, 8.
7, 8, everybody agree? Because 7 is the number being subtracted from x, and 8 is the number being added to the function,
Yeah.
right? So we would just go down here and go 7, 8. Okay? Okay, I already did that one. Did that one. I want to get a couple more here. Oh, come on, give me a new one. There's one. Okay, look at that guy. Now, this is really strange. This is called a reciprocal function, and it's got some weird characteristics. One thing I just want to point out, just because it's kind of interesting based on some other discussions we had, we'll come back to this later on in the year. Do you see, are there any asymptotes associated with this graph?
Yes.
There are.
0.
There are. One of them is at x equals 0.
Oh, and the y.
And y equals 0. And y equals 0 and x equals 0, right? Both axes are asymptotes. If I scoot way off to the right, the y value is going to stick to 0. If I go way off to the left, the y value will stick to 0. This has got a horizontal asymptote also, which we haven't seen yet. You know, if an ant backs down towards 0 from the right, he goes up this infinitely tall slope.
The closest he's
Right.
going to get is 1, 1.
Say it again.
The closest he's going to get to 0 is 1.
Well, he could never get back to 0. He can get as close as he wants to, but as he gets closer, he's from the right, he's going to get shot up infinitely high, right? And that peak never ends. It always gets continually steeper. So there is a limit to his motion here. As he goes from the right, he can never get to 0. We've never seen a function like that before. When he approaches 0 from the left, the same thing happens, but now he's going down. None of that is particularly crucial to us right now. I just wanted to point that out. I mean, we've seen these things. Here's a function that has them. Let's look at what we're dealing with now, though. Based on this parent graph, so f of x is just f of x equals 1 over x is the red function that's graphed. Where's the special point this time? I mean, it's same place, right? The dot is on the origin. That is not even on the graph, though, is it? Right? The graphs are here and here. That point is not a part of the graph. It's just there because even though it's not on the graph, it's still the most important point to sketch this graph, right? That special point is where both of the asymptotes intersect. And the asymptotes, like later on, one of the things we're going to be doing here, you might have guessed this, is we're going to be doing things like, okay, I want you to make a sketch of that graph, right? And we'll be doing other things other than just translating it. We'll be stretching it and reflecting it, doing all kinds of crazy stuff, right? But we always want to start off at the special point. Well, this time the special point is going to be the place where we'll draw the asymptotes, and then we'll be able to just kind of fill in the curve based on the asymptotes, right? So where is the special point going to be this time?
0, 0.
Well, it starts at 0, 0. But how about for g of x?
-8, -2.
-8, -2. How'd you get to -8? You're right.
Because it's just like the opposite of what it is. 'Cause
Okay.
Y is, or the X is opposite.
Okay,
It's
-8
horizontal.
is the number being subtracted from the input, isn't it? Right? Everybody agree?
Yes.
Okay. And -2 is the number being subtracted from the whole function, right? So we would know that the coordinates would be -8, -2, right? That's going to be where, if we wanted to graph this thing, here, let's put it on Desmos and see. I'll show you what I mean. Now, what did I think of this before?
Yeah, mine would be 13 inches. Yeah.
You might have to go to someone else, because.
Sorry.
Okay, so what about this, right? Let's graph these two. So if I graph the parent function, f of x equals 1 over x, there it is, right? There's the function we're used to seeing. Okay, right? What, you getting all that? There's our parent graph. So now let's make g of x. Let's start off with the same thing. Oops, that's not right. Oh, yeah, I did. Okay. Equals. Oh, man, I got this all messed up. I'm just starting over. This is a mess. Oh, there we go. Okay. There's 1 over x. Okay, let's do a couple things. So to the outside of the function, if we subtract 2, look what it did. Okay.
Whoa.
Yeah, it took everything and just moved it down by 2, didn't it?
Yep,
Right?
You need to go lefty.
Okay, so now if we go over here, and adding 8 is the same as subtracting -8, right? What'd it do?
Moved it over.
Yeah. Yeah, it moved the whole thing. Everybody agree? It moved the whole thing. So here's our special point right now, isn't it? Right?
Yeah.
It's back 8, down 2. Well, x minus -8. We could do the same thing by just
Do you
saying.
have to do that?
Do what?
The minus.
No, no, we can, let's undo that. That seems complicated. X minus negative 8, I just want to make the point that that's the same thing as, there you go, plus 8, right? You get the idea? But everything else is the same about it, right? These functions look identical, except for where that center
So
point
in
is, the
Desmos,
special point.
You don't have to change it to -8 like right then.
No, you shouldn't.
That's
You
what
shouldn't. I was just making the point that we're subtracting the h value, which is -8. But you guys already get that, it seems like. Okay. All right. So we're getting there. Now let's come down here. Let's take a parent function of absolute value specifically. Try this one. Okay, so this time I want you to choose the graph corresponding to an absolute value function. I'll remind you, and on the assignment, for every one of these, I give you a little bit of information right above the question that reminds you for now. That's what an absolute value parent graph looks like, right? F of x or y equals the absolute value of x is a V shape. Where's the vertex? That vertex always means kind of a point, right? So the vertex is at the origin, so that's our special point, is the vertex. Normally we would go over one to the right and up one, or back one to the left and up one, right? Okay? So there's our parent graph. Now I want you to pick out pick the graph corresponding to that then. So where would the coordinates of the vertex be for this one?
Left 4 and up 2.
Left 4 and up 2, so -4, 2. We just want to find a regular, a V-shaped graph whose vertex is at -4, +2. That's really all we're doing, isn't it? So -4, right there.
Bingo.
Right? That's it. Okay? You get the idea?
Yep.
Okay.
No, it's actually making sense.
Good.
I don't know why it wasn't, because it's actually pretty simple.
Oh, it is, but you have to make some connections.
Yep.
Now, what if let's turn this around now. The other thing I'm going to have you do is I'm going to give you an absolute value graph, and I want you to write the absolute value
Well, I can
function.
do that.
Okay, so what's that going to look like?
Um,
So we'll start with absolute
Parentheses.
value. How about? Oh, and how do you get absolute value? You could go down here and just pick the absolute value bars. That's fine. I'll just do that. Or if you use the little vertical symbol that's right above enter, if you hit shift /, that gives you a vertical line. You can also use those. Okay, so what's going to go outside of the function? I'm starting off with just the absolute value of x. Let's do the vertical shift first.
Up 3.
Up 3.
3.
Okay, so the y-coordinate of the vertex is at 3, so I got to put a +3 at the end, because that's plus k, right?
You put +5.
Okay, everybody agree?
Yep.
The x-coordinate is going to be -5, and so I'm going to have to subtract -5, which is adding 5.
Bingo.
So that's how I'd fill in the blank
That's
there.
why it does that. It's because it's 2 negatives.
Yeah, exactly. There it is. Okay, so here's what I want you to do now then. I want you to open those up, and I want you to go to the 2.1 Practice 2 assignment, and I want you to do problems 5 and 11. 5 and 11. That's good. Yeah, number 5 and 11 on the 2.1 Practice 2 assignment. And then if you get done with those successfully, you can just keep working on it because it's going to be homework anyway. Get some stuff out of the way.
The internet is not working very
Start recording again here. Okay, I'm going to Desmos, and we're going to take a parent function. We're going to go ahead and use absolute value of x because it's so easy to work with, right? So I'm just going to go. I can go shift, vertical, and notice when I put in that vertical line, it gives me 2 of them. So there's my absolute value function. Agreed?
Agreed.
Everybody agree? Okay, so what I want to do now is, instead of translating this thing, we're going to try some other stuff. What do you think? Anybody want to make a suggestion how I could take this function and I could stretch it out vertically? So we could start with a function like this, and I could take everything and just stretch it up vertically and make it taller and skinnier. Let's make it twice as tall as it originally is. What's that going to do? So in other words, I want the vertex to still be at 0, 0. But if I go over 1, Let me zoom in a little bit so we go by ones on our scale here.
How do you get twice as tall if it's 0?
Okay, with that, well, what's two? I mean, you couldn't get twice as tall there, could you? But when I go over 1 and up 1, instead of going over 1 and up 1, I want to do the point, I want to go over 1 and up 2. I want to go through that point. And instead of going over 2 and up 2, I want to do the point over 2 and up 4. I think oops. Like that. How am I going to do that?
I don't know.
Any suggestions?
Somehow you gotta like narrow it down here.
Yeah, so I'm going to go ahead and take, let's start with the square root of x. Now the green overlaps the red perfectly, and let's do something to that function.
Like, you could do 1/2 x.
Okay, let's, I could,
No,
actually.
You need to
But let's do
add
something.
1 so that it goes back over here, so then it's up like that.
Okay, so I could do a 1/2 x, but that's way ahead of where we want to go. For now, I want to do something to the whole function. What if I put a 2 out front?
Oh.
What do you know?
What happened?
Okay, look what it did.
Because that's quite the same thing as that, right?
Okay, so now let's think let's always think about this in terms of what did we just tell the math gods to do? We told them we're going to take a regular square root of x function, right? And when we calculate an output from that, what are we going to do to it? We're going to take 2 times the output of the normal function. Well, output is y value, isn't it?
Yes.
Right? Wyatt, you getting this?
Yeah.
Right here, right here. If square root or absolute value of x is our normal output, if I multiply that by 2, I'm taking all of the output, the y values,
Cut it in half.
multiplying them by 2. And so instead of going over 1 and up 1, so instead of having an x value of 1 and the corresponding y value of 1, now we go over 1 and we get 2 times 1 is 2, right? Okay? So what if I wanted to squash it down? Let's say this time instead of going over 2 and up 4, let's say this time I want to go over 2 and only go up half as far as I normally would. I want to go up 1. What could I do? Let's make a new function, call it h of x.
Now you go half?
Yeah, I could go half. I could say equals 1/2 times absolute value of x, and look what it did, right? So what can we say then? We could say that if we are going to multiply a function by a number, if I want to stretch it, I have to multiply it by what kind of number? Well, okay, how big? Over 1, greater than 1.
Yeah.
If I want to shrink it, I'm going to multiply it by
Under.
less than 1. Okay, but I'm going to throw one more crazy thing at you here. What do you think is going to happen? Let's call this j of x. Real quick here, we'll get you out of here. But what happens if I multiply the whole thing by -1?
It goes on the bottom. Underneath.
Crazy. It flips it. How about that? All right.
Request me, Mr. Williams?
Yes. Oh, who wants to be requested? Raise your hand if you want to be requested.
I'll be requesting.
Okay, actually come right up here real quick if you want to be requested. Make sure I get you.
Trent.
Here.
Okay. So I got Trent, Wyatt, Zach. Gotcha. Kenzie, I got. Wyatt, we need. Anybody else be requested?
Yeah.
Okay. Want to be requested? Okay. Already had you, Shane. Yep, you're set.